Any questions about anything before I cover more? Your papers are due up through Monday. In other words, don't come complaining to me after Monday. You've had all semester. And I have received one. The first one is in. Thank you very much. Friendly reminder, again, this is where you really reread those instructions. Just make sure you're doing everything I'm asking so you don't get docked points. But one that usually people forget at the end is send it to me electronically. But I'm asking for a hard copy as well. So you can print it out and bring it Friday or Monday. Or before Monday, as long as it's up through Monday. But most people tend to bring it Monday in class, but you can do whatever you want. So, yeah, it's due Monday.
And you want it single spaced, right?
I think I said that, didn't I?
Because that's what the example was.
It's not, I can't remember what I said. It's not crucial, whether it's single or double. It takes up less space single, but I don't care. The type, the digital, so I can read it and analyze it. But I grade the paper one. That's what I'm looking at when I'm marking up. So I guess double space would allow more room for comments, but I'm wishy-washy on that. Don't forget your works cited. You need to report your sources. The example has been on WebAssign, yeah, from the get-go. That was one of my favorites. I thought really well done from last year. She agreed to let me post that. That way you had something good to see and have a clue what it was talking about. I know somebody complained, can we get more examples? Well, you're lucky you got an example. Last year they didn't have an example, but have fun with it. That was my point. Again, my main point of it is I find the best way to learn this stuff is to try to explain it. And writing a paper, I thought, would be a fun way to do that. You learn a lot more when you have to turn around and tell someone else. You know how I've been periodically saying, how would you define this to your mother? How many have ever actually, after this class, gone out and tried to explain one of these concepts to your roommate or sister or brother? Kudos to you. Did you find that helped you understand it better, or at least find the holes where, oh, you start trying to say it and you fumble over your words. Oh, I guess I don't get that quite right. Yeah. That's what I was trying to do. And hey, if you guys have suggestions of other ways I can do that in the future, I'm all ears, because I learn the best, I know, by trying to tell someone else what I thought was cool. So, other questions, concerns? Oh. Your homework is due Sunday night like normal. However, be forewarned, the one after that, let's see, so that's homework 8. Homework 9 is now available for you also. It's going to be due right before class next Wednesday, because we review next Wednesday and have an exam over all this next Friday. Not this Friday, but next Friday. So it'll be due in the middle of the week, in the middle of the day. The due date's there when you forget, but because you have a little less time, you now have access to it, so you can be working on it also. Yes?
I have one question on the homework. There's one question where it gave you like 3 different frequencies, and it said which of these, they give you 4 choices of 3 other different frequencies, and which of those frequencies matched up, or
Was that the beat frequency thing?
beat frequency. I couldn't find in the book how to figure that out. So we can kind of go over that. So I'm not sure how to do the beat frequency thing.
Oh, right. Chapter 20 at the end, which we haven't covered yet in lecture. And you haven't read that far either then. Yeah, it's on this homework assignment because I'll be through it before it's due. But yeah, we haven't covered beats yet. But yeah, the very end of chapter 20, if you want to jump ahead and look at that. They even give you an example. Basically, it's the difference between the two frequencies that are happening. Create beats. It's a superposition of waves. All right. Doppler effect. That's what we did last time. At the very end. Raise your hand if you hear two notes. Oh no, what happened? I'm sorry. You should hear that. Or if I go faster, we can do it with higher frequencies. Anyway, that's the Doppler effect. Because this is fun to, or actually hard, fun sarcastically to draw, I got an animation for you. So I'm going to turn that on and show you. The Doppler effect is a change in frequency of a wave due to the relative motion between a source and a receiver, the thing that's making the sound and the detector, usually our ears. And so if this blue dot up here is a source, it's emitting sound at a certain frequency. We'll simplify, it's one frequency. Nice pure sine wave. And so it emits radially, and you get these wave fronts. Think of those wave fronts as compressions of air. That reminds me, while I'm on, when the air compresses, whoosh, what do you think happens to the pressure there? It increases. And when it rarefies, rarefaction, whoosh, spreads apart, the pressure drops. So you can think of them as, that's why it's called a pressure wave. But yeah, it's compressing, stretching, compressing, stretching. Think of, if it helps, think of those wave fronts as a compression. That's where the pressure's high. Okay? And the air is going like this. The medium is vibrating. But the wave propagates. Not the medium, but the wave. Okay. So if you have a source and it's not moving and we're not moving, that's what it looks like. Exciting, huh? But if you drag it, whoa. If it starts moving while it's emitting, they don't make concentric circles anymore. It's not symmetric. On the right side, the wave fronts are closer together. So what happened to the wavelength? That's right. They got smaller. They're closer together. Think of yourself. Let me do it again. Think of yourself as where the cursor's at, that arrow on the left. Do you hear any sound yet? Do you hear sound yet if you're at the cursor? No, because no sound waves have reached you yet. It has a certain wave speed, speed of sound. But now, boom, 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 boom. The frequency is increased because it's reaching your ear more frequently because the waves are closer together. But now, as the source passes you, boom, 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 boom. Oh, it stopped on me. The wavelength increases. It's less frequent. The frequency decreases. So in front of the wave, it sounds like that frequency that the source is emitting is higher. And as it goes away from you, it sounds lower. Yes?
So that means it's a lot louder.
He asked, I want to, I'm glad you asked, because a lot of people are thinking that. So I'm going to address the whole class. He's asked, so when it's coming at you and it's more frequent, does that make it louder? Raise your hand if you think so. Raise your hand if you don't think so. And that's why we use clickers, because 3 of you are voting. All right. The frequency is unrelated to the amplitude. And the amplitude has to do with its loudness. It's how intense it is, which we'll discuss even more next chapter. So it's not louder, but it'll sound higher pitched. Higher pitched, not higher in volume.
That won't be faster either. Like say you have a radio that was going like that, you won't hear the sound faster, which is just the pitch.
Good question. Yeah, if that was a radio and it's coming at you, it wouldn't sound louder, but all the frequencies would be shifted slightly higher. And so it'd sound more like, I didn't plan this, honest, Mickey Mouse or the Chipmunks. Like you're playing it back a little quickly because they're reaching your ear more quickly.
So the speed of the song would pick up then?
The frequencies are higher.
But not, like the song still would be 3 minutes.
It's a good point. The Chipmunks, they actually sped up the song, didn't they? Okay, scratch that. Bad example. That's what I get for doing it on the fly. The frequencies are definitely shifted. Yes. Yeah. And on the other side, it'd sound lower. So more simplistically, if that's a note vibrating at 440 hertz, that's concert A. How many of you are musicians, by the way? 2, 3, 4. So you know what I'm talking about. 440 hertz. That means it oscillates 440 times a second. That's the A, and kind of in the middle of the piano. If you keep bouncing that out, but you're in a car coming at the piano, you're coming together. So will that shift up or down? The frequency you hear? Up. Because they'll reach you more frequently. And it might shift and sound like, depending on how fast you're moving, 444 hertz. Even though the person's still plucking at the same rate. The string's vibrating at the same rate. But the waves reach your ear more frequently. You're not magically changing the sound source. But you hear, definitely, a different frequency.
I have a question.
Yeah.
So what would the waves look like with a sonic boom? Are they all the waves?
I'm glad you asked. Sonic boom. Let's do it. So the wave source was moving, but going slower than the wave speed, the speed of sound. That's when we hear the Doppler shift. This one's a little faster, and you can see that the waves on the right are bunched up even more. That would be a bigger shift, a higher shift in frequency. And now, as it passes you, an even lower shift in frequency. What if you go even faster? Let's go the speed of sound. There's a little, in the upper left, upper right, a yellow. It's the ratio between the speed of the blue wave source, the blue dot, and the speed of sound. If that ratio is 1, you're going the speed of sound right there. Oh, close enough. Boom, boom, boom. He's still emitting at the same rate, but look what happened to the wave fronts on the left now. They're all bunching up and overlapping. It's a superposition. They're not interfering with each other, but if you were right at that position when just use the word, Adam. It's a bow wave. It's starting to bunch up. Your book defines it. Let's do it again. The blue dot is moving the same speed as the waves it emits, the speed of sound. So they move together. And the wave fronts on the right are all moving together on top of each other. So if that wave passes you, like where my cursor is, oh, it'll stop before then, won't it? There? You would hear all of them at once, and it'd sound loud, like a sonic boom. What if you're going faster than the speed of sound? Now you can get ahead of the waves you're emitting. You're traveling faster than sound. So you can see what happens. You kind of get a cone shape, a V shape. And this wave again, this front on the left side, the wall that it forms, do it again. So I don't hear anything, don't hear anything. You know, you see the airplane going by, but you don't hear it yet. And then all of a sudden, boom, they all hit you. That's a sonic boom, makes a V. Bow waves, your book defines as like this, two-dimensional. They make the V shape, or like a speedboat in the water. You've probably all seen that, the waves behind a real fast speedboat. They can form a V shape. A shock wave is just conical. Instead of being circles that spread out, they're spherical. And it forms a cone behind it. That help? So yeah, you can be going less than the speed of sound, or faster than the speed of sound. And that'll shift how the waves overlap when they approach you or recede from you. Here's another way to see it. Yes?
Can this be used to demonstrate the effects of whales and dolphins in the water using sonar to communicate with each other?
Sonar, like with whales and dolphins. No. That's more just echoes, sound reflecting, or a bat. It emits a sound, it goes out, and then it reflects off of this person. Comes back to the person, and you can tell how far away they are. It does apply, though, they do use it, but not Doppler effect is involved, but it's more about the echo. They can detect people. If they want to detect their motion, though, that's where the Doppler effect comes in. For example, if you are running away from me, then I send out a frequency, a wave. It reflects off of her and comes back to me. I detect it. But if she's moving away, then can you see that the waves that will be coming back to me will be farther apart? A lower frequency, though there will be a Doppler shift there. And bats and porpoises and whales can detect that. And the amount of shift tells us the amount of motion. So yeah, you can spot someone and tell which way they're moving and how fast. And that's extremely useful and definitely the Doppler effect.
Okay, well, and submarines use the same.
Submarines do the same thing, yeah. Yeah. So do cops with speed guns. Policemen. Is cops derogatory anymore? I don't know. Same idea, different simulation. So here the source is on the left, the observer's on the right. But you can see the waves up top. The waves emitted from the source are a nice sine wave at the top. Certain frequency. You can gauge that by the wavelength. The observer is detecting the same thing. Now if we move the source, whoops, there. Now you can start to see that the wave fronts, boom, 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 got shorter, this section, higher frequency, smaller wavelength as it was approaching. But now, look, they're farther apart, the lower frequency, because they're getting to the observer less frequent. So review, that's a stationary source. Here the source is moving less than the speed of sound. We'd get the Doppler shift. If you're moving the same speed as sound, you get that superposition of wavefronts, and they all line up. And if you're going faster, you start getting that V shape or cone shape. There's a picture of a bullet on the right. You can actually see the shock wave. That front right there. That's where these waves are adding up and lining up. Does this all make sense? Hopefully? Yeah.
If you're traveling at the speed of sound, if you travel at the speed of sound for longer, is the sonic boom bigger than if you just pass the threshold really quick?
What's your gut answer to that?
I feel like it would be bigger if you stack up more waves. But
Yeah, if you maintain going the speed of sound or faster longer, and you think it'd be louder, well, it all ends up on that front. The waves all stack up like, we'll just repeat this one over and over. And you can see it like at the beginning, when it starts over, there, boom, boom, boom. You don't hear it as well. But if you're over here, the wall runs into you. Boom! But let's say you keep traveling at that same speed for farther to the right. Well, you've already heard it. It's past you. So you won't hear it again. But somebody that's up here will hear it, but they'll hear the same thing you did until it passes them. Even though this guy's maintaining going that fast for longer. Question for you, though. Do you think the pilot hears it? No, yeah. The wavefront doesn't pass him, does it? He's in the cockpit. Or she. So, you can do this. Get in your car. Honk your horn continuously, moving sound source, right? You can see on the left here is the camera and a microphone. There's one in the car as well. Do you hear a Doppler shift? So where's the microphone for this video? Inside the car. You're moving with the sound source. So there's no shift because there's no motion between you and the horn. This one, different. Now the camera doing the videoing is not where the source is at. You're moving relative to it. And so as you approach, it sounds higher, and as you pass it, it sounds lower. And another. Now we're on the ground. And the car passes. And you can hear it again. So it comes at you, it's higher. Lower. I think there's what's going on here? The sound source is stationary. There, we're on the same, the horn's going, but we're standing next to the horn. We're not moving with respect to each other, so there's no shift. So it doesn't matter if the source is moving or the receiver or both, as long as there's relative motion. If you're coming together, increase in frequency, apart, decrease. So my all-time favorite bumper sticker, and I need to put a new one on my car because it came off. It's been on for years. But it says, if this sticker is blue, then you are driving too fast. So I can tell who gets it by how many chuckles there have been yet. So that's why I'm pausing. In theory, this is on the back of a car. You're driving up to it. If this sticker is blue, you're driving too fast. Doppler effect works for any type of wave, not just sound. Light is a wave. And which has a higher frequency, red or blue? Blue. Blue has a higher frequency. So if you're looking at normal light, or red light like this, if you're approaching, do you expect the frequency to shift up or down? Up. So red light should shift to a higher frequency. If this shifts to blue, you've shifted up almost the entire visible spectrum. So you must be approaching really fast. Why it's really funny is because you have to be going at least like 40% the speed of light to even see this effect, in which case you have other problems, but you get the idea.
Well, I was just going to ask, yes, I get the whole...
It's about 40%, yeah, which is really fast. Not possible with our current cars. But the point is, the Doppler effect works for light. We can detect stars that way. How do we know the universe is expanding? Redshift. What's redshift mean? Explain that just a little.
The universe is expanding, so all the light sources are also moving out, and as a result they have lower than...
Yeah, if they're moving away from us and expanding, then the Doppler effect says the frequencies are shifting down. So any light we see gets shifted down, a decrease in frequency, like to the red side of the spectrum. If it's shifted to the blue, we know we're approaching. You can determine how fast something's spinning, like this. The difference that it shifts up and down tells you how fast it's going. This is approaching you, so it shifts up. This is going away from you, so it shifts down. If this is a star and it's rotating, right? And you detect the light from this side being blue shifted and this side being red shifted, you get a different spectrum from over here and over here. You can determine how fast it's rotating. And they do. And that's enough of that. Okay, I'd like a volunteer, pretty please. I need help with this. Thanks. So enough of Doppler effect. That's superposition of waves. They overlap. We're going to overlap some more waves and review that interference stuff. So if you'll hold that end over there, I'll hold this end. Why don't you come back this way towards the table a little. Yeah, there we go. All right. What's the source of all sound?
Vibration.
A vibration. It's the source of all waves. So vibrate away. I'll hold still. Perfect. So he's creating a wiggle in time, but it's propagated through the medium of the spring. There's a wave speed. And a wave travels to me and reflects back. Can you send like just one pulse? A non-periodic vibration, where you just pulse it once. Yeah. Then we can see it reflect, or you can even do this. Doink, 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 doink. You can see it going back and forth, right? Yeah. If we can continuously drive this vibration, not just a pulse, but a train of pulses, and they reflect back on each other so that it constructively interferes. Remember what that means? The crests are both up at the same time. They're not out of step. They're not out of phase or out of step, but they match up at the same time. So if the wave going one way matches with the wave reflecting back, you can get something special. You want to try it? So start driving. Keep going and see if you can get it to line. Oh, there it is. There's one right there. He's a natural. This is called a standing wave. We also say this is resonating. It's at resonance. It wants to vibrate like this. It's easy once you got here, isn't it, to keep it going? It requires less energy to keep vibrating like this. How long is this wavelength? Roughly, compared to where we're standing. 3 meters. How about compared to the distance between us? What's a wavelength? It's from crest to crest, from parts where it cycles through. Here, like right now, when this side's up, you have a crest, and on that side you have a trough. So where would the next crest be? Just past him. So we'd have to go from this bump. You can rest. It's beyond him. But another way you can think of a wavelength is it's a crest and a trough. One complete cycle, right? So in that case, one wavelength was the distance between us. Do you see that? It was a bump up and a bump down. That is one wavelength. If I vibrate like this, now what's the wavelength? It's twice the distance between us. Because at any given time, it's a crest only, trough, crest, trough. But right there, while it's up, you have half of the wave between us. And so the distance between us is only a half a wavelength. Are you with me? A whole wavelength would be twice our distance. But this is another standing wave. The wave goes that way, reflects, comes back. Reflects, goes back. Reflects. And they superimpose and they interfere constructively to create a standing wave. All right, see, can you get more than 2 bumps? Go for 3 bumps. Will you have to vibrate more frequently or less frequently? More frequently. So go up and down faster. A lot of people naturally want to do it harder and increase the amplitude. So that if this was a sound, it'd be louder. But this is the same frequency. It's still vibrating at the same rate. There's only 2 bumps. So he needs to go faster, not harder. That's a good increase in amplitude. Oh, now you're getting it. Yeah, do that. Faster, faster, faster. Up and down, up and down. All right, you take a breather and you hold still. Let's see if I can get it. Oh, that's too many. There we go. I've hit resonance. So now the wave traveling back and forth between us, the incident wave and the reflected wave are matching up, and you get 3 bumps. What's the wavelength now? Not 1/3. 2/3, because you need a crest and a trough. 2/3. And you see it's going up and down faster. The frequency's higher, wavelength's shorter. All right, go for 4. Now what's the wavelength? Half. Another standing wave, good. All right, go as fast as you can. Hey, see, now he can do it. He's got, is that 3 or 4? Close to 4, yeah. There, resonance and a standing wave. Now, it's called standing because it appears to be stationary if you go super fast. And you see the points in the middle that look like they're not moving much? Those are called nodes. I'll draw it on the board, but they're called nodes. All right, you rest and I'll do one more. Another standing wave. Ooh. You see the frequency's higher and the wavelength's shorter. And you see the spots in the middle now, they might be more conspicuous, the nodes. Okay, that's good. Thank you very much. Give him a hand. What the heck? That didn't sound good. So say I send a wave that way to the right. It reflects back. When it comes back, it looks like the dotted line. They match up. Because then it goes back again and it's in phase. It's in step. Constructively interferes, and we have a standing wave. And these points are called the nodes. They are the points of minimum displacement. You can touch right there on the spring, and you don't dampen the motion, so it can still continue. But if you touch, say, here or here, that's where it's trying to vibrate. Maximum displacement. We call those antinodes, the X's. That spring could vibrate in several different modes. Let's see. Let's draw a few. So we're going to have nodes here. We have to in this case because we were holding each end, right? Trying to, you can have one like this. Mode 1. And we call that the fundamental frequency. It's the one that requires the least amount of energy to resonate. And when we give a pitch and we go, la, we say, oh, you just sang a such and such note. At what frequency? We're referring to the fundamental frequency. So when you pluck that piano string that's 440 hertz, the A, that's the fundamental frequency. However, at the same time you pluck it, strings, just like that spring, can vibrate at this and higher multiples of resonance too at the same time, generally with less amplitude. The next one this one could do is if there was a node in the middle. We saw that. It reflects back on itself. And that'd be the second harmonic. This is in your book. Why is it called second? Because that's the first. That's where we start. The next one would be the third. You get 3 bumps. All of these miraculously can be vibrating on a piano string, for example, at the same time. And they'll all superimpose to make a non-sine wave. But it's still periodic. It might look like something like that, where they all try to add on top of each other, superposition. But they're standing waves. They're superimposing and interfering with each other. How many nodes are here? 2, 3, 4. What's if this distance is L? What's this wavelength? 2L. So you got a crest at one time, and then it reflects, and now it's a trough. But at one time, it's a crest, and you'd have to come over here to have a complete wave. So yeah, this wavelength, whoops, is L. 2L. This one is L. And this one, 2/3 L from A to B. That'll help with a lot more of our waves as we go on. Now, we can only hear certain frequencies. I like this one. I think you will too. Our ears are only can only detect certain frequencies. The range is 20 hertz to about 20,000 hertz. It varies slightly for different people and as we age. So I have a function generator. This emits sine waves, specific frequencies. An amplifier so we can hear it, and a speaker. I do that because I love this. This still runs on vacuum tubes. It takes a while to warm up. Yes, Brian?
Should have brought a sander or a scanner so I could see it.
That would be good. Sorry. Future reference. You can come up closer and feel the low ones if you'd like. Feel the speaker. What I'm going to ask you to do is I'm going to start at 20 hertz. And I want you to close your eyes. No, that's not fair. Leave your eyes open. Raise your hand when you can hear sound. And when you can't, be honest, put it back down. When you think you can't hear this anymore, put your hand back down. And I'm going to span this range. And it's interesting to see, because everybody has a different range. Do you want to come over here and feel it? Maybe you can. Okay. So I just want to, seriously, you can hear that? I can't, but I'm older. Oh, now I can. Right there. Okay, let's keep going. I'm going to adjust the volume as we go because this gets annoying, but can you feel that, Brian? Can you feel that, Brian? That's 20 hertz. It's not a great speaker. That's 50 hertz. So you can't hear it? Oh, you're just not playing. Okay. I'm going to pause there.
I can hear that.
You can hear it? I'm going to pause it. That's great. Because I had my hand up to show you I wasn't adjusting the volume there. Our ears are more responsive to that frequency. There's, so to speak, more resonance. They're more sensitive to that range, which was about 3,000, 3,500 hertz. And there's a reason for that. We'll discuss more. But not all frequencies to us sound the same loudness. That was the same volume and intensity. I didn't change it. But it sounds louder to us. Because when something resonates with you, it rings true and louder. I mean, there's truth to that saying. Let's keep going. I'll turn it back up. I'm going to increase. Does it sound quieter to you already? Okay, I'll turn the volume up. Whoop. That high frequency. Now be honest. Tell me when you stop hearing it. And where are we at? Oh, look at that. 22,000 hertz. That claims it's 20, assuming this thing's accurate. Can anybody hear that? My daughter can. It annoys her. Yeah, I hear nothing. See, Brian, I'm like you. I hear nothing right now. I can hear that. Okay. So that's our range of hearing. I think that's fun. So about 20 to 20,000 hertz. All right, let's clicker time. All right, I'm logging in now to get the session ID number. There it is in the bottom right, like normal. What we got? 5 minutes? That'll work. So while you're logging in, next time we'll do more of Chapter 20 with beats. No. Yeah. Forced vibrations, more about this resonance and standing wave stuff and how it propagates through different mediums. But again, friendly reminder, your paper's due Monday at the latest. Check out the 2 homeworks you now currently have open. And let's start. Okay, polling is open. In the United States, if you're curious, electricity is at 60 hertz. In Europe, it's 50 hertz.
I missed the session ID.
Oh. 513 787. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 71% think it's A. Good job. Good job. I'm glad you're getting the relationship between frequency and period, that they're inverses. For those of you that did miss it, 50 vibrations in 1 second. Vibrations per second, cycles per second, hertz. So it is 50. That's the rate that it's vibrating. Okay, go. So you're making ripples in water, and you decide to do it more frequently. Boom, 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 boom. What happens? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, bless you. We're getting it. 88% said B. You're right. What I want to emphasize here, too, is what's not changing? Can anybody guess what's not changing here? What? I'm hearing whisperings but can't make it out. Yeah, the wave speed, the velocity that it's traveling. It's still in water. That medium, sound travels so fast in water. That doesn't change. Remember the formula? Velocity equals frequency times wavelength. So if the velocity is staying the same and you make it more frequent, the wavelength goes down. Same with our spring here. The wave speed didn't change in all those instances because it's the same spring. So it travels the same speed through this medium. But we changed the frequency and the wavelength. How could I change the wave speed through this? Any ideas? Tighten it. If you increase the tension, like in a guitar string, then they're more tense. And that wave can propagate more easily. And it does. That would change things. So if I were to stretch it, keep it in the same length. Could also change the length between us. Things that are smaller generally like to vibrate more quickly. We'll go over that more also. Ready? Go. What's a standing wave? It's produced by reflected waves doing what? What makes it the standing wave? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. I know there's somebody else out there. Oh, well, you missed your boat. Whoosh. Well, we're split now. Most of you think a change in frequency. Since we're out of time, it's interference. What makes it a standing wave is, remember the incident waves? Bump up, reflected wave, bump up or down. They're interfering and create that standing wave pattern. What changes the frequency is how fast you vibrate it. But it's still waves reflecting back and forth and how they add up and superimpose. It's about interference that makes a standing wave. Okay, See you Friday.